Yeah. All right. Hey, this afternoon I wanted to continue on with what I started yesterday. So, yesterday I argued to you that the basic science of liquid crystals involves understanding both the magnitude and the direction of the nematic order. And today we've heard mostly things about the direction. But I want to go over in the lecture this afternoon about what determines the magnitude of the nematic order. And in particular, I want to present to you a theory for that, known as Myers-Alpha theory, which involves predicting both the magnitude, which I defined as S in the lecture yesterday, and also to calculate the isotropic to nematic transition. And you'll recognize that the isotropic nematic transition is a special case of determining the magnitude, right? Because that's a transition which is going from S equals 0 to S not equal to 0. Okay? This is a classic order-disorder type of transition, right? We're going from the isotropic phase, which is a phase that has more symmetry, or equivalently less order, to the nematic phase, which has less symmetry or more order. So this is within the class of things that Mark Bowick was speaking about this morning, right? And so we have here our fundamental system, the Hamiltonian that describes the molecules in a liquid crystal, is isotropic, right? There's nothing special that singles out any direction compared to any other direction. In that case, in the language of group theory, right, Mark would say that the symmetry group is SO3, right, something that's isotropic in all directions in three-dimensional space. And it's getting broken down. We're picking out one particular direction as an axis of the nematic order, and then there could still be symmetries of rotations about that one direction, right? And so now we only have a limited set of rotations that are symmetries, so that's what Mark would call SO2. Okay, so we want to understand what determines this symmetry breaking and how much the symmetry is getting broken. Okay, and you can recognize that when you have a competition between order and disorder, that here we have to think about a competition between energy and entropy, right? So that the state that has less order is one that is favored by entropy. That is, there will be more entropy associated with the isotropic phase. There are more microscopic states that are equivalent to each other in the isotropic phase. In the nematic phase, there's less entropy, right? So why would the thing form a nematic phase? Well, it must be for reducing the energy associated with the structure, right? That in the nematic phase, there are more molecules that have the favorable alignment with respect to their neighbors, and hence this nematic is favored by energy. And so when you combine the energy and entropy together to form the free energy, as you will recall from statistical mechanics classes, right? It's the energy minus temperature times entropy. And so when you're at a low temperature, this temperature times entropy is not so important, right? And so energy will control things. We get a pneumatic phase, an ordered phase, right? When you're at a high temperature, this entropic piece becomes more important, and hence it tends to favor what's favored by entropy. That is the disordered phase, the isotropic phase. Okay, now I've got to apologize for something here, a problem that I cannot solve. Right? The problem that I cannot solve is that the letter S is universally used for entropy. The letter S is also universally used for the pneumatic order parameter. So I'm stumped. What do I call things? So I'm going to put a little subscript, like entropy there, and S pneumatic here. So this guy is a pneumatic order parameter. This is entropy. These are not the same thing. These are totally different things, right? And so I'm going to try to avoid confusion, but I can't change the letter because that's just what everybody uses. Okay, so what we want to do is minimize the free energy to figure out how big is the pneumatic order parameter and whether it's 0 or not 0. In general, that is a very hard calculation, right? In general, that is a calculation which is impossible to do exactly because the system has an enormous number of degrees of freedom which are all coupled together. And there is no way to integrate over the partition, to integrate over all these degrees of freedom to get a partition function and the free energy exactly. Okay? But there is a type of approximation which is very powerful, and that is called mean field theory. This is not exact, right? This is an approximation, and the key to this approximation is to neglect correlated fluctuations of the molecules or any other particles in general, right? So we are going to pretend as if each molecule is fluctuating independently of its neighbors, and that there's some characteristic one particle distribution function for these fluctuations, okay? And as you will see, this tremendously simplifies the problem and allows us to calculate many properties of phase transitions. Now, of course, we're not calculating them exactly. We're calculating them at some level of approximation, but it's a good start, right? And then we can try to work from there. Okay, so my goal is to do this all for the isotropic pneumatic transition. But in order to get there, I want to do a warm-up problem. Okay, I want to try to do exactly the same kind of calculation for the Ising model, which Robin and Mark have already discussed with you. And that will demonstrate some of the main principles, and hopefully I can get through that quickly and then move on to the isotropic pneumatic transition. Okay, so let's begin with the Ising model. Okay, so this is a classic model for magnetism. It was developed, I guess, in the 1920s by Hans, it's a German graduate student, Hans Ising, right? As a German, he pronounced his last name Ising. He was a graduate student at the time, and this is the only case I know of where work was named after the graduate student rather than the professor. I promise you this will never happen again. Okay, so he pronounced his name Ising, but American physicists consistently mispronounce it as Ising, and you know, you've got an American lecturer here, so take what you get. All right, so the idea in this model is that we have a lattice of spins, okay? And each of these is either pointing up or down. So you have some picture like this, okay? So this is going to represent a magnet where each site is some local magnetic moment. And a local magnetic moment that can point up or down. And then there can be a Hamiltonian, right? So the energy for this system is determined by the interaction of all these different spins, right? So each of these, spin number I, is represented by a variable sigma I, which is plus or minus 1, okay? And these things interact with their neighbors, and they also interact with some applied magnetic field, H, okay? So the energy of interaction is, for the interaction between the neighbors, is going to be a sum over all nearest neighbor pairs, okay? So this notation with sum over in angle brackets, I comma j, right? So I and j each represent sites, and when I put them between angle brackets, that's shorthand for meaning the nearest neighbor pairs, like these two spins, or these two. Okay, so the sum over that, sigma I, sigma j, okay, and then there's an interaction with the applied field, which looks like minus h times the sum over all these sites of sigma I, okay? So, what you'll notice here is that this first term favors having the two spins aligned with each other, right? This is minimized if sigma I and sigma j are both plus 1 or both minus 1, right? If they are both plus 1 or both minus 1, then this term is going to be 1, and so that you get an energy of negative j, right, which is good. But if they are opposite to each other, if one is plus 1 and the other is negative 1, then they multiply to give negative 1, and they make an energy of plus j, right, which is a high energy. It's bad. Okay, so that's the interaction term. Okay, and then we have the way that the spins individually interact with an applied magnetic field. Okay, and so if the field is in the positive direction, it favors spins in the positive direction and disfavors spins in the negative direction. Okay, so far so good? All right, so now we want to try to figure out what's the energy and entropy associated with different states of the Ising model, to find out whether the free energy, defined up there, is going to favor having alignment, some net magnetic order, or no alignment, just 50-50 up and down. Okay? So, in order to do that, let's start with the entropy. Okay? So, for the entropy, that involves counting states. Okay? So, let's look at this. Suppose that we have here n spins on this lattice, and each of them can be either up or down. Right? So, the total number of states is going to be 2 to the n. Right? And now I want to classify the states based on what's the net magnetic moment. Okay? So, we'll say of these n spins, we have n up and n down, right? Some of them are pointing up, some of them are pointing down, okay? and I want to classify all the states based on the average magnetic moment, right, which is, the average is n up times plus 1, right, plus n down times negative 1, all divided by the total n. Okay, so from this, I can easily figure out for any particular value of m, how many ups there are and how many downs there are, right? Because this equation is n m equals n up minus n down, and the total n is of course just equal to n up plus n down, right? So this is two equations and two unknowns, and so that means, right, that n up is the total times 1 plus m over 2, and n down is the total times 1 minus m over 2. All right? So now I want to know what's the number of states with a particular value of m, of states as a function of m, right? Well, this is a standard combinatorial problem, right? It's the binomial coefficient of n choose n up, right? Or it's equal to n factorial over n up factorial n down factorial, like that, okay? And then that's just what I need to get the entropy. All right, so for the entropy, you remember from statistical mechanics classes, right, the entropy is the log of the number of states, right, multiplied by Boltzmann's constant, okay? So the entropy, right, as a function of magnetization is Boltzmann's constant times the log of the number of states. Okay, so Boltzmann's constant times the log of n factorial over n up factorial n down factorial. All right, so now we can work this out, expanding the logarithm and using Stirling's formula, right? If we use Stirling's formula, that the log of n factorial is approximately equal to n log n minus n, okay? So I'll do this, I'll do all the calculation. I don't really want to go through all the algebra, okay? But suffice it to say that this all works out to the answer, which is minus Boltzmann's constant times n, and 1 plus m over 2 log 1 plus m over 2, right, plus 1 minus m over 2 log of 1 minus m over 2, like that, okay? So this is an expression for the entropy. I know I skipped a bunch of steps to get from there to there, but they're sort of straightforward steps. Why don't you try doing them for homework, and if you have trouble, just come talk to me. Okay, and so you'll recognize this expression, by the way. This is like the fraction of up spins times the log of the fraction of up spins. And this is the fraction down times the log of the fraction down, right? And the sum of fraction times the log of that fraction. This is a sort of standard information theory sort of expression for entropy. Right, okay. So this makes an expression for the entropy as a function of the net magnetization, right? An order parameter for the magnetization. And this just came from combinatorics, right? Just from counting states. Okay, well, that's the entropy. What about the energy? Okay, well, for the energy, here, I want to take the expectation value of what's up there. Okay? So, for the two terms in the energy, the second one is way easier than the first one. Okay? So, for the two terms in the energy, right, I'll look at the average like that. Here, I'll do the second one first, because it's easy. Okay? The second one has a term of minus h, okay, times the sum of all these spins, okay. Well, that's just equal to this number of sites times the magnetic moment, right? That's just this thing right there, okay. That's easy because it doesn't involve any interactions between different sites. It's a sum of single site properties. Okay? The second one is hard, right? Because it involves some expectation value of the nearest neighbor interactions, right? And so if I wanted to calculate that exactly, I'd have to say, well, if this guy is plus, you know, what are the chances that this one is going to be plus or minus, right? This one is probably going to be influenced by its neighbor over there, okay? So here I do mean field theory, right? I say, let's pretend as if they are fluctuating independently so that they each have their own distribution, right? They each have some expectation value of m, okay? So the product of them is just going to be m squared. Right? That's a reasonable approximation to start with. Okay, so I'm going to have, for the interaction term, a minus j times m squared. All right, and now how many terms like this are there, right? Well, how many nearest neighbor pairs are there in the lattice, right? Well, the number of nearest neighbor pairs is equal to the number of sites times the number of neighbors that each site has, divided by 2, right? Because if I didn't divide by 2, I'd be double counting, right? I would say, well, this guy is neighbors with this, but this guy is neighbors with that. Okay, so I will say it's the number of sites times the number of neighbors per site. Let's give that the letter Q. The word for that is the coordination number. All right, divided by 2. Okay, so this is a mean field expression for the energy. All right, so now I can combine these two things to make the free energy for the Ising model. Okay, so the free energy is going to be the energy minus temperature times entropy. Okay, so minus NJQ over 2 times m squared minus NHM, okay, plus n times KT times this messy looking thing. 1 plus m over 2 log 1 plus m over 2 plus 1 minus m over 2 log 1 minus m over 2. All right? And if I want to make things look simpler, I could just divide out something to reduce complications. Let's see. I'll divide out n, because every term here is proportional to the number of sites. And indeed, the free energy should be proportional to the number of sites. Okay? So, here's a nice expression for the free energy. And now, in mean field theory, I can ask what value of the magnetic ordered parameter minimizes this free energy. Is it going to be positive, negative, 0? Let's find out. Okay, so we have a nice function here. It's a function of m with parameters that are jq and h and kt. All right, so let's just try plotting it up in Mathematica. All right, does this work? It worked a minute ago.
Is the projector on?
Well, it was. There it is. Okay, so here it is. Okay, so here in Mathematica, I plot these things. All right, so here's the entropy. Okay, and you can see the entropy looks a lot like an upside down parabola, approximately. Right, so there's the most entropy for the magnetic order parameter equal to 0, and it decreases. The least entropy is when it's either +1 or -1. Okay, and then what else do we have? Here's the energy down below it. Okay, so I've got the equation for the energy, and that's a pretty simple equation, but of course, you know, we can plot it. So here, the energy looks like an upside down parabola, and I can tune it with this nice manipulate command in Mathematica to change the j parameter or change the h, right? And as I vary h, it changes what the symmetry of the curve looks like. So let's combine them into the free energy. Let's combine them into the free energy here, all right? So here you recognize the expression for the free energy that I tried to work out over there. And so now let's plot that as a function of m. Okay, so here is the plot, and with this manipulate command in Mathematica, right, I can adjust the j parameter or the h, the magnetic field, or the temperature, right? This is meant to look like little knobs in an experiment. So, suppose I'm at high temperature, okay? If I'm at high temperature and I vary the magnetic field, right, you can see that at positive field, I get some positive magnetization. When it's 0 field, I get 0 magnetization. When it's a negative field, I get a negative magnetization. Right? So it responds approximately linearly to the applied field for small field, and then it saturates at a maximum value. Okay, so now let me put the field back at 0. Whoops, and I'm going to put the field back at 0. Okay, and now suppose I reduce the temperature, right? And as I reduce the temperature, you can see that the minimum at a magnetic order parameter equals 0 is getting flatter and flatter, right? It favors 0, but that's getting flatter, and at some point it breaks up. And so that minimum breaks into 2 minima separated like that. and that is the spontaneous symmetry breaking, right, like we've been hearing about from Mark. Okay, so that is an example where we can see that behavior, and we can see that there's some favored value for the magnetic order parameter, and it's moving away from 0 as the temperature decreases, like that. It's getting pushed towards plus or minus 1. And what if I had a magnetic field? Right? Well, if I had a magnetic field, if it's a positive field, it makes the positive magnetization state go down, go lower in free energy. If I have a negative field, it makes the negative magnetization state be lower in free energy. Okay? And then I can, try to write things down in a lab notebook, right? I'll write in a lab notebook, at a certain field and temperature, this is my minimum, right? And then I vary the field and temperature and see what's the new minimum. Or I can make Mathematica and do all that work, and I can generate lots of the magnetic order as a function of field. Or I could generate plots of the magnetic order as a function of temperature. Or I can be really cool and make a 3D plot of both things. So here's my 3D plot, okay? And so here, what you can see in the three-dimensional plot is that there is a nice smooth surface, right? This is a plot of the magnetic order parameter as a function of temperature going from high to low, and magnetic field like this, right? And so at high temperature, everything is nice and smooth, right? But if I come down at 0 field, reducing my temperature, then there's this singularity. There's a critical point where spontaneous symmetry breaking occurs, and the system can go to a state with positive or negative magnetic order. And if it's 0 field, then it randomly chooses one or the other. But if the field is a little bit non-zero, then that determines which way things go. And so there, the symmetry is getting broken, and so there's no more phase transition, it just evolves going up this way. So this kind of behavior at the critical point for 0 magnetic field is what's called the second order phase transition, right, where the symmetry is getting broken and the order parameter continuously moves away from 0. In mean field theory, it moves away from 0 as a square root law. And then the behavior as a function of magnetic field at low temperature is a first order phase transition, right, where there's some discontinuity as h passes through 0. Okay, so that's my quick little story about the Ising model. Okay, now, Robin.
Did you say anything about what dimension we were in? You drew a 2D picture, but there's no D in that.
That's right. In mean field theory, the dimension only enters through the coordination number, q, right? So for a square lattice in 2 dimensions, that would be 4, right? For a cubic lattice in 3 dimensions, that would be 6, right? And so in mean field theory, dimension is not very important. It will just change the numerical value of the transition temperature that gets calculated. That is not true in a more exact theory, right? In more exact treatment, dimension can be much more important than that in determining properties of the phase transition. Mean field theory is working pretty well at high dimension and less well at low dimensions. Another question?
The coordination number also, I mean, that if you don't assume periodic boundary conditions, then that won't be the same for all lattice sides.
Oh, yeah, for sure. If you have some finite system, then there will be different behavior right at the boundary. right? And so there might be extra order or reduced order depending on what happens at the boundary. And that's a very interesting subject, which I'm not going to talk about right now. Great. Okay, what if we want to do the same story for liquid crystals? Okay, so let's try it. Let's see. So here, my corresponding story for liquid crystals is called Meyer-Zalpa theory. I don't actually have any funny stories about Meyer and Zalpa, but I did get Zalpa's office at Kent State, so that's my connection. All right, so for Meyer-Zalpa theory, here we imagine that we have a box filled with liquid crystal, okay? And so there's a whole bunch of molecules in here. And these molecules are characterized by some orientational distribution function, which can be represented by a nematic order tensor, like I defined for you yesterday. Okay, so hopefully you remember. And so now, the whole point of our calculation, right, is going to be to figure out what is the free energy as a function of that nematic order tensor, to see whether the minimum is going to be when that tensor equals 0 or not 0. So, in order to do that, I want to do the same kind of thing with figuring out energy and entropy as functions of the nematic order parameter. And in order to do that, I need some microscopic model for what are the interactions, okay? So I'm going to say that each molecule interacts with Q neighbors. So, you know, they're not really on a lattice, but on average they have Q neighbors in space around them. And for the interaction between them, the interaction has to be something which favors nematic alignment, right? Favors having them be parallel to each other. So we could say if there's some angle between them that is theta ij between molecule I and molecule J, then the interaction ought to be minimized when theta is either 0 or 180, right? And maximized when theta is 90 degrees, perpendicular alignment. Okay, so the Meyer-Zalpa assumption is that this energy of interaction between I and J is some negative J, some interaction parameter, times P2 of cosine theta ij. For this P2, it's the second Legendre polynomial that I was telling you about last time, and this is equal to 3/2 cosine squared theta ij minus 1/2. Okay, so there is actually a nice way to derive this interaction by looking at quantum mechanical fluctuations of electrons on the molecules. You could say if electrons are fluctuating up and down this molecule, and then it induces, it makes a polarization, and that induces a polarization on the neighboring molecule, and this polarization and this polarization interact with each other. right? It's the same story that you've probably seen in derivations of the van der Waals interaction in colloid physics, right? This is a sort of anisotropic van der Waals interaction. But I don't have time to tell you where this comes from. Let's just assume it's true. Okay, so if this is true, now let's figure out things about energy and entropy. Okay, so let's again do entropy first. Okay, so for entropy, what I care about is what is, minus temperature times the entropy, all right? And so I will here draw inspiration from the equation that's up there, right? Up here, we see that the entropy for the Ising system, right, where there are two possible states for each molecule, up or down, right? It's the sum of probability times the log of probability over these two states. Now, for the liquid crystal molecules, there's more than two states. There's a whole infinite continuum of states, right? Each molecule could be pointing in any direction in three-dimensional space, right? And so instead of just having probabilities for up or down, I've got to have a whole probability distribution function as a function of theta and phi, right? The coordinates in three-dimensional space. Okay? So I have this orientational distribution function, which is a row of theta and phi. And so my entropy is going to be minus T times entropy is going to be kT times N, okay? And then an integral over all the solid angle of rho of theta and phi times the log of rho of theta and phi. Okay? And for the integral over solid angle, you remember that this is an integral of sine theta d theta d phi. Right? That's how you do integrals in solid angle, in spherical coordinates in 3D. Okay, so this is an expression for the entropy in terms of the distribution function. Okay? Now, that's not quite what I want, right? What I really want is an expression in terms of the nematic order parameter. Okay? So, here, I will make a guess for what's the orientational distribution function, right, in a nematic state. Okay? I will guess that there is some kind of effective potential in the nematic phase. Some effective potential that looks like effective potential V is something proportional to this P2 of cosine theta, right? That favors alignment of theta, let's say in the plus or minus z direction. And I'll put on a coefficient for the strength of this effective potential. I'll call it U. And let's make U dimensionless. So I'll normalize everything by kT. Okay, this is my guess for an effective potential. If I had more time, I can actually prove this is true, but I don't want to take the time to do it, okay? So just trust me on that one, okay? So if this is true, then can say, what is the probability distribution function, this orientational distribution function? And it would be rho of theta and phi is something like the Boltzmann factor, right? The exponential of the effective potential over kT. So e to the u times p2 of cosine theta divided by the normalization, the integral of e to the u p2 of cosine theta, sine theta d theta d phi, all like that. Okay, so this is my rho, my orientational distribution function, and so now I'll put it into the integral up there to get the entropy, in terms of the u, this unknown variational parameter, okay? So in that case, the entropy minus T times the entropy is equal to what? It's equal to KTN, okay? And I've got a rho log rho, and rho is this ratio, okay? And so now in the log rho part, I'll break it up into the part with the numerator and the part with the denominator, okay? So I'll have an integral of rho of theta and phi times the numerator part. The numerator part is going to be a u times p2 of cosine theta, right, times sine theta d theta d phi, okay? And then I'll have the denominator part, and so that makes a minus KTN integral of rho times the log of the denominator. Okay? Okay? And so each of these things simplifies reasonably well, right? In the in the second term, right, here we have the log of the denominator, right? Well, the log of the denominator is just some constant that factors out of the integral, right? And so it factors out of the integral, and then I just have an integral of the probability distribution function. So it just integrates to 1, right? So this last term is minus KTN log of the denominator. And that's all. Okay? And what about in the first term? Well, in the first term, here we have our KTN, and if I factor out this u parameter, then what's left is an integral over the probability distribution function of P2 of cosine theta, right? Well, you recognize that, right? That's how you calculate the averages of things, by integrating that thing times the probability distribution function, right? So that makes the average of P2 of cosine theta, and that average of P2 of cosine theta is just what we mean by S, the pneumatic order parameter. Okay, so my expression for this entropic contribution comes out to be this KTN times US minus the log of the denominator. This denominator. Okay, so that's my entropy. Better figure out the energy before I run out of time. All right, so for the energy, where can I put it? Put it here. Okay, so the energy, the average of the energy is, so minus the J times the number of interacting pairs of molecules, which is NQ over 2, times the average of P2 of cosine theta ij, the relative angle between two molecules. Okay? This average is what? Well, it's the average of 3/2 Li dot Lj squared minus 1/2. Right? Because this dot product is the cosine of the angle between them. Okay? So, I will write this out in my nice tensor notation as, I'll make it 3/2 times the average of Li alpha, Lj alpha, right? That's the dot product written in tensor notation summed over the index alpha. You guys claim that you've heard tensor notation before, right? Okay. If you have questions, ask me. And then make another copy of it because it's squared. So Lj beta, whoops, Li beta, Lj beta. This thing minus 1/2, okay? And now I've got an interaction between two neighboring sites, right? And now's the time when you worry. How do you calculate this average of two neighboring sites when one influences the fluctuations of the other one, right? Time to use mean field theory, right? Here comes our mean field assumption that these things are fluctuating independently of each other so that we can neglect those correlations. And so this is approximately, at the mean field level, equal to the average of Li alpha, Li beta, right? Properties at the site, or of the molecule number I, times the average of Lj alpha, Lj beta, properties of molecule number J. Minus 1/2. Okay, almost there. So now we say, let's relate that to the nematic order tensor that I told you about yesterday. Okay, so the nematic order tensor is pretty much that same thing, right? So the nematic order tensor, Q alpha beta is, well, 3/2 L alpha L beta minus 1/2 delta alpha beta, right? And now you say, well, the L alpha, L beta for which molecule? Well, all the molecules, they're all the same, right? So it works for molecule I or molecule J or whatever molecule, right? And so the L alpha, L beta is, whatever it is, 2/3. 2/3 Q alpha beta plus 1/3 delta alpha beta, right? And it's for any molecule. And so I can take this thing and plug it into here. So the average energy is going to be 3/2 of 2/3 Q alpha beta plus 1/3 delta alpha beta, right, for site I. Then the same thing, 2/3 Q alpha beta plus 1/3 delta alpha beta for site J, minus 1/2. So this is a little bit of tensor manipulation, but I'll skip to the bottom line here, right? Oh, and I forgot this other thing in the front, that times, this whole thing times minus J and Q over J, right? Okay. So this whole thing in the end, this whole factor works out really nicely. This whole factor is just S squared. It works out to be just proportional to the pneumatic order parameters squared, because it's one site interacting with another site. So 2 powers of it, right? And then this makes a minus J n cubed over 2 times S squared. All right, so now I'm in business. I've got a free energy. I've got all the pieces I need for a free energy that involves 2 things. It involves energy and entropy, right? So the free energy is minus J n cubed over 2 S squared, okay, plus the entropic piece that's up there, okay, plus KTN times US minus the log of that denominator, which I probably erased by now. So, you know, I'd like to have it written as a nicer function instead of the log of this integral, but, you know, it's life, do what you can. But, you know, the only thing that differentiates special functions from messy integrals that you have to do numerically is that special functions have already been named after somebody. And so, you know, if this one didn't have a name, I could just call it the Stellenbosch function, and then you'd say the answer is the Stellenbosch function. Okay, so here, let's do things, all right? So in Mathematica, the first step is to relate S to U, right? Because S is the expectation value of this P2 of cosine theta. I was hoping I could call it the Stellenbosch function, but Mathematica can actually do it in terms of the error function like that. Okay, so be it. All right, so this is the S in terms of U, all right? So then if I keep going down, I can work out what's the energy, that's 1/2, minus 1/2 JQS squared. Okay, so here is a plot of the energy. Oops, what did I do? Here is a plot of the energy somewhere near the top. All right, and so you can see that the energy is favoring large U, large S, right? And that makes sense. That's what we think is happening, right? That the energy favors large pneumatic order. Okay? And now, what about the entropic term? Well, here I calculated it, I plotted it actually with a factor of -t in front. So this is a plot of minus T times the entropy. And so that contribution to the free energy is minimized here, right? So the entropy is favoring 0 nematic order, right? And then I can combine them to make the total free energy and plot it, okay? So here's a plot of the total free energy, and now I can manipulate what's the ratio of the interaction strength divided by kT, okay? So this is a plot at large, at small interaction strength, right, or large temperature, and the minimum is here at the isotropic state, right, at 0. Now, as I dial up the interaction strength or reduce the temperature, you can see how the plot evolves. And you can see that now the system develops a different minimum, right? So here is a stable minimum in the isotropic phase. Here, a metastable nematic minimum, okay? And as I continue to reduce the interaction, to increase the interaction strength compared to temperature, or reduce the temperature, at some point, whoops, I'm doing the wrong guy. At some point, the states become equally deep, okay? So here, there will be a phase transition, right? At this value of JQ over KT, there's a phase transition from isotropic to nematic, and at even lower temperatures, the nematic is favored, and nematic becomes more and more favored as I reduce the temperature. And so by going through this, we can figure out where is the nematic minimum. And in fact, I can program Mathematica to search for the nematic minimum as a function of temperature. And this is the bottom line, right? So plotting, so with this model, we can say for the nematic order parameter S, as a function of temperature, right? What you get by minimizing that free energy function is 0 at high temperature, and then there's a discontinuous jump up to a non-zero nematic order parameter of about 0.4. And then as you continue to reduce the temperature, it continues to get bigger and bigger until it would saturate at a nematic order parameter of 1. Okay, so I'm about out of time, so let me just wrap up with the main point to take away from this, right? Well, the points are, one is that in general, in statistical mechanics, right, there's this trade-off between energy and entropy. And that trade-off determines what amount of order there's going to be in a broken symmetry state. Right? It determines what's the phase transition temperature, and then if you are in the ordered state, it determines how big the order parameter is going to be. Okay? So that's one thing we learned from it. Another thing we learned from it has to do with the order of phase transitions. That is it a second order transition with a continuous evolution of the order parameter, or is it a first order transition where there is a sudden jump in the order parameter? And so for the Ising model, this mean field theory predicts the second order transition. For Myers-Alpha theory, it predicts a first order discontinuous phase transition. And finally, you might be asking, well, where's the prediction for the orientation of the director? Right? I've predicted the S, I haven't predicted the orientation N, right? And that's the point of spontaneous symmetry breaking, is that there isn't a prediction for the orientation of the director. It could point in any old direction, right? So the temperature, the competition between energy and entropy, strongly determines some magnitude of the pneumatic order, but it doesn't at all determine the direction of the pneumatic order. So the direction of the pneumatic order is determined by all the little things that we haven't considered yet, like surface anchoring or applied fields. Right? That's what makes the direction easily changeable, while the magnitude is difficult to change. It's only changeable through temperature. All right, I think I better stop here and invite questions, and then I can continue on with my stories in the next lecture. Robin?
You had a field in the calculation for the ICAMP model, but you conspicuously left out the field for the pneumatic. Is it possible to include it in this calculation?
Sure. Yes, it would be possible to include a field, and that would make a model for pneumatic order under an applied field, and so at high temperature, that's called the Kerr effect. That applied field induces a little bit of pneumatic order, and at low temperature, there isn't really a name for it, but the field would change the pneumatic order parameter a little bit. Not very much, just a little bit. And if there were a high enough field, then the discontinuity would get smaller and smaller, and eventually there would be a critical point where the discontinuity goes away. And all that, I'm confident, could be done by putting a field term into this model, a small modification.
Thank you very much. Any specific questions to this? This way. Not.
If anyone cares, I can put the Mathematica up on Facebook, and I think Facebook may have a special Mathematica module or something. Thank you.
Thank you very much.